Okay, so स्क्रीन नजर आ रही है आप लोगों को?
Yes, sir.
Okay. So let me begin. Today's lecture will be built on the concepts of previous lecture, and that lecture was about particles. So we discussed Newton laws, kinematics of a single particle. So, and you also know that the original formulation of Newton law is also for a single particle. So today we need to investigate how we go from one particle to a rigid body. So as I told you before many times, a rigid body can be viewed as a system of particles. So if you have a rigid body um, and you have a system of particles, so you can label each particles. Wait. Yeah. Okay. So. Okay. 7. What is it? 7. What is it? 8. No, I think something is wrong. So, okay, I can maybe use the screen. Is this screen visible?
Yes, sir.
Yes, sir.
Okay, because I somehow am trying some shortcuts and now I forgot the shortcut for red. So, okay, so if we label these particles as 1, 2, up to n, and the idea is to, if it is a rigid body, even if this object moves as a whole, or if it rotates or spins, the distances between these particles, they're not supposed to change, because if they change, then it will deform, and the rigid body is not supposed to deform. So now the idea is to replace this rigid body with a single particle where all the mass is concentrated here. So all the mass will be here. And instead of 1 to up to n, we'll just call it C. C is the center of mass, okay? So the center of mass can be thought of as a single particle where all the mass is concentrated. And if we can do that, then we simply apply Newton's law on this particle rather than on all of these particles separately. How do we go about it? For that, let's say I start with particle I, and with that particle, maybe I need to change this. Yeah. So now this will be red. So I have this particle I, and on this particle I can consider the different forces. So I can say, okay, the net force, external force on particle I. Okay. Now this because I'm saying net because it will be a. I think in this slide we don't need to consider the forces. Okay. So I think there is something we discuss in the next slide. So here we simply develop some terminology. So for this mth particle, the mass will be mi. Yeah, obviously for particle I. Position vector will be ri. Yeah, ri. Velocity will be vi, and momentum will be pi. These are all different labels, so I can replace I with 1, 2, up to n. And the total mass m. And when I say total mass m, that m is simply the sum of all masses from 1 up to n. So the idea about the center of mass is that if it is a rigid body, and if I take the moment of each particle, let's say this is this particle C, the abstract particle C, which I'm looking for. So you also know, I mean, instead of center of mass, you may have heard center of gravity. Yeah, it's a related concept. So if I imagine different forces of gravity acting on all of these particles, yeah, they together, the moments should be balanced by the moment at this particle, and that calculation can be done here. Okay, you know, this equation only has a missing g. So if g was there, then you are basically taking the moments. And because I'm writing ri minus rc, let's say this is this some reference x y z, and this is your o, and this is rc, and let's say that is ri. So ri minus rc means that I'm calculating this moment about the point C. Yeah. So zero moment about point C means that that is a real center because all the moments cancel out there. So if I solve this equation, I get the position vector for the center of mass. Yeah. In most cases, it will be equal to center of gravity. So you just see, I just take the moment of masses, yeah, and then I divide it by total mass. So this mass, if this is my O, now this RC is the position vector of that center of mass. So now once we do that, then I can talk about the motion of the rigid body. So you know the motion is quantified by momentum. So m will be the total mass. Yeah, m will be the total mass. And instead of tracking these individual velocities, I can prove that I can simply track the velocity of this point, Vc. C is the center of mass. So I can now easily replace a collection of particles by a single particle. And from now onwards, all the Newton laws, so now we can develop the Newton law for rigid body. Okay, Newton law for, so how to go from rigid body to um, how to go from particle to a rigid body. So I can now go back to that picture and I say, okay, I have these different particles, 1, 2, up to n, and I just focus on particle I. On that particle, if let's say if this is the system, so I can say, okay, F-I-E-X-T. So this is the external force, which is the vector sum of all external forces acting on particle I. Similarly, these internal particles, I mean, they will also apply force on this particle I. So let's say this is the net force internal to the system on particle I. Yeah, if internal. That is again a vector sum of all the internal forces. So if I want to apply Newton's second law on particle I can simply say mass times acceleration for particle I, and it will be the net force, which will be the total external force on that particle, the total internal force on that particle. And because my actual goal is not to write the equation for a particle, but for this whole rigid body, I can now sum all these forces over all particles, sum, and now I can see something, that this summation will actually be zero. Yeah. Why? Because all the internal forces, they must come in pairs, and according to third law, they will just cancel out. Okay. And this total net force, this will, I can just simply write Fext for the external force. Yeah. And this expression can be simplified by choosing a single particle at center of mass with total mass concentrated there, and the acceleration calculated at the center of mass. Okay. One student in the other lecture asked me, why is this not zero? Because these forces also come in pairs. So how would you answer that? Why is this not zero? Anyone? Because that pair, those pairs will be made with systems out, particles outside the system or bodies outside the system. and our system is this body, okay? So we are writing an equation for this body. So this, even if this cancel out, that will be another equation, and if we increase the scope of our system to include those bodies only, then it will be zero. Okay. So this cancellation will not happen if we if for example this was our system, maybe that force doesn't cancel there. So this cancellation only, remember in my last lecture, I gave you those two scenarios that if I have two particles inside a system, these forces will cancel out. But if this is my system, for example, if this is my system, then the force from this particle on this particle, this will not cancel out. Yeah, because now this is my system. Okay, so external forces don't cancel out. If they cancel out by chance, that will be simply because they are balancing. That is not because they are action reaction. ये बात समझ आ जाएगी? So what is the summary from these two slides? That we can, by the concept of center of mass, which is nearly the same as center of gravity, इनमें जो फर्क है वो बहुत ज़्यादा एडवांस्ड टॉपिक्स में आपको नजर आएगा, इस तरह स्पेस शिप्स और तो लेकिन हम उन डिटेल में नहीं जाना चाहते. For all practical purposes, center of mass and center of gravity are the same, and this concept allows us to go from a system of particles, which is a rigid body, to a single particle. So हम सिर्फ center of mass पे ही forces और सारे वो apply करते हैं, ठीक है? And we can easily write Newton laws of motion. इसको हम चाहें तो आप इस फॉर्म में भी लिख सकते हैं mvc dot, yeah? vc dot. Yes. So the next topic is a new perspective on the kinematics, equations of kinematics for a particle. You must have studied these three equations in ये जो आप स्कूल में भी पढ़े होंगे, कॉलेज में भी पढ़े होंगे, and they are called equations of motion. ठीक है, गैलीलियो ने ये डिस्कवर किए थे. Can somebody recall the condition for all these three equations? कि ये तीन equations which type of motion is described by these three equations? Condition उसमें क्या था? Constant what? There was something constant under which these three acceleration. Yeah, constant acceleration. ये आपको A नजर आ रहा है इसमें ना, ठीक है? So now we need to think about these equations of how you would derive these equations such that they can be generalized. So for example, if you look at this equation, you can derive this equation from the definition of velocity. You know velocity, if I take the vector, is the derivative of position, yeah? Exactly. So how would you solve this equation to find a change in velocity? A change in velocity, v final one, v minus initial. What would I do? I will, sorry, this is wrong. A change in I think the equation I wanted to have in mind was not this one. It was this one. The acceleration. The acceleration is the rate of change of velocity. Okay. So if you want to solve this equation, you integrate. Maybe I should write it in this way. Okay. I can write it in this way: that rate of change of velocity is equal to acceleration. I can now integrate both sides over time. Yeah, and on left hand side, the integral of v dot is vf minus vi, ठीक है? And the integral on the right hand side will be something like this, between t1 and t2, or ti and tf. And if acceleration is constant, you simply write a times t, or tf minus ti. ठीक है, बट इफ दिस a was not constant, फिर आप क्या करते, बताएं मुझे। यहाँ पे a of t होता, a of t, तो फिर आप क्या करते हैं यहाँ पे? You can still express this as something times tf minus ti, but this will not be the acceleration because that is a time dependent quantity. This will be the average acceleration. क्या? Every integral can be written in the form of the average quantity multiplied by the length of the interval. This is the interval. So you can see this as an integral of acceleration over a time interval. Can you recall from calculus the theorem which allows this? Calculus में कौन सा theorem है जो ये allow करता है? Where you write an integral in the form of an average times the interval. कौन सा theorem है, बताएं मुझे। From calculus. You must have heard this. Mean value.
Some mean value theorem.
Yeah, mean value theorem. ठीक? So if you want to replace this equation for situations where the acceleration is not constant, all you need to do is to change this with the average, okay? Average acceleration, and then you are fine. लेकिन यहाँ पे जो मेन हमारा मकसद था वो क्या था? हमारा मकसद ये है कि हमने we viewed this equation as an integral of acceleration over time. Yeah, so which means that acceleration can be integrated over time, and it gives you change in velocity. It gives you change in velocity. What if I multiply both sides by m? How can I reinterpret this? How can I see this as an integral of something and it gives me a change in something? क्या बता सकते कि यहाँ मैं क्या लिखूं? ये क्या है? I can see this as the integral of force, और यहाँ पे क्या हो जाएगा? The change in momentum. ठीक है? So integral of acceleration से हमने इंस्पायर होके एक नई क्वांटिटी डिस्कवर की है जिसको इम्पल्स कहते हैं। क्या? Impulse. Now why is impulse more practical than force? Because force, the action of a force cannot produce any effect if there is no time. So time आपको interval चाहिए t1 t2. So basically force को जब तक आप over some time interval integrate नहीं करेंगे आपको effect नहीं मिल सकता. So impulse is the integral over time, and that is more practical because that gives you the change in momentum. ठीक है? ये बात समझ आ रही है? Okay, how we see this equation, the second equation of motion, S equals Vf plus Vi over 2 T. किसी को याद आ रहा है कि इस equation, इस velocity को हम क्या कह सकते हैं? Which velocity is this? V? Give me a name.
So average velocity.
Okay, average velocity. तो अब let's see how would you have derived this equation. Okay, आप क्या करते? Distance के लिए क्या है कि speed, let's focus on speed, velocity को छोड़ रहे हैं फिलहाल. So speed is the rate of change of distance, yeah? Yeah, and I can integrate both sides. So on left side I will write s2 minus s1, which is s, yeah, and on left hand side, on right hand side I'll simply say v dt from t1 to t2. अब आपको पता है कि यहाँ पे एक acceleration constant है ना, a is constant. If acceleration is constant, then v cannot be constant, yeah, v is not constant. ठीक है. When v is not constant, I need to apply mean value theorem. तो ये क्या हो जाएगा यहाँ पे, जो पहले फॉर्मूले में बताया था, t2 minus t1, the length of interval of time, and v will be replaced with v average. अब आप कह सकते हैं कि मेरे पास तो यही फॉर्मूला आ गया, तो इसमें तो कांस्टेंट एक्सेलरेशन नहीं है. इवन अगर ये एक्सेलरेशन भी कांस्टेंट ना होता, ठीक है, तो आई कुड स्टिल हैव रिटन दिस इक्वेशन. तो फिर इसमें और इसमें क्या फर्क है? व्हाई डू वी नीड अ कंडीशन हियर? कोई बता सकता है? इस इक्वेशन के लिए तो मुझे कोई कंडीशन नहीं चाहिए था ना. डिड आई यूज द कंडीशन ऑफ कांस्टेंट एक्सेलरेशन हियर? नो, आई सिंपली अप्लाइड मीन वैल्यू थ्योरम. मेन पॉइंट इसमें ये है कि हियर इट्स द एवरेज वेलोसिटी. एवरेज वेलोसिटी का एक्सप्रेशन हर दफा ये नहीं होता. ये जो एक्सप्रेशन है ना, when you say that average velocity is vf plus vi over 2, ये सिर्फ constant acceleration में valid है, ठीक है, क्योंकि velocity increases linearly with time, and that's why you can take this as your average velocity, ठीक है, velocity time graph. So what we discovered here is that we can integrate velocity over some time interval and we will get distance, and when we integrate acceleration over time interval, we get a change in velocity. Okay, this was pretty straightforward. And if we combine these two, so let's say eliminate t from these two equations, yeah, combine these two so that you eliminate t and you will get something like this. This is your third equation of motion, and let's see how can we see this as an integral of something. So आपने नोट किया कि जब आप यहाँ when you saw a times t, you saw this as an integral over time. So if you see s here, a times s, this you can see as an integral of acceleration over, बताएं क्या होगा, over d what? d distance, ठीक है, and this is along some path. So you imagine a path. अगर एक्सेलरेशन कांस्टेंट है फिर तो पाथ नहीं है, फिर तो स्ट्रेट लाइन है, ठीक है. लेकिन अगर ये जरूरी नहीं है, यू कैन हैव एनी काइंड ऑफ मोशन जिसमें एक्सेलरेशन कांस्टेंट ना हो, फिर ये इक्वेशन वैसे भी गलत हो जाता है. देन यू हैव टू रिप्लेस दिस साइड बाय इंटीग्रल a ds, okay. And if you want to write this in vector form, remember I can imagine any point here, and if this is the tangential force and this is dr, the displacement, and this small displacement, so I can say, okay, acceleration, yeah, displacement, integrate, and this gives me this change in v squared over 2, yeah, v squared over 2 का change है ना, ये vf squared minus vi squared, I can think of this as v squared over 2. Now I can multiply both sides by m, yeah, m. अब ये m चाहे मैं इधर लिख दूं चाहे मैं इधर लिख दूं, m मैं यहां पे भी लिख सकता हूं. So this gives me another insight that I can, and because ma is force, so I can now imagine a quantity or an integral of force over displacement along some path, yeah, in space between any 2 points, let's say point 1 and point 2, and that will give me a change in, तो बता सकते हैं ये change किस चीज में है? Change in, बताएं. That was a change in momentum when we introduced mass. This is now a change in kinetic energy, ठीक है. So we, just by looking at these equations and by thinking about them, we introduced two new quantities, the integral of force. So I can now summarize this. The lessons we learned from kinematics of a particle is that we discovered that the force is not as useful as the integral of force over time, and that is a useful quantity, integral of force over time, and that is something we know by the name impulse. Okay, impulse. And we also discovered that the impulse causes a change in momentum. So if you apply impulse, this will give you a change in momentum. Similarly, this was integration over time. Similarly, we discovered from the third equation of motion that the force, when integrated along a path in space, gives you another more useful quantity, and that quantity we remember by the name work. We call it work. So work or moment, impulse, S and EI, they both represent the accumulative effect of forces. और हमें ये भी पता चल गया कि एक पर्टिकुलर एग्जांपल में this gives you a change in kinetic energy. ठीक हो गया? Can you ये बात तो एक स्पेशल केस है जिसमें ये चेंज इन काइनेटिक एनर्जी की बात हम तब करते हैं कि we know that between point 1 and point 2 the velocity has changed. Okay, velocity यहाँ पे vi था, यहाँ पे vf है, वो चेंज हुआ है, तभी हम इसकी बात करते हैं. There are examples where you don't change the velocity or the velocity doesn't change and you still have to work. तो उसमें then you have to find out कि ये change in whatever. ठीक है ना? So let's say we consider the example in a gravitational field where you raise a body from one point to another point 2, and let's say ये जो height है ये height h है, and you can say okay r1 r2. ठीक है, r1 r2. So again you need some force here, and you will see this integral, the work done on this particle, that will result in a change in. अब देखो, let's say imagine that you raise this object in such a way that the velocity here and the velocity there is the same. So v1 equals v2. Velocity change नहीं हुआ. When the velocity didn't change, so this work caused a change in some other form of energy. और वो form of energy यहाँ पे क्या होगा इस example में? Potential energy. Expression क्या होगा उसका? mg h. So it's not always the case that work will lead to a change in kinetic energy. In this case, it gave you a change in potential energy. So a more general statement is that a work can cause a change in energy. Okay. There is even a third example where the work will lead to a change in some other form of energy. Let's say, ये आपने सोच के बताना है मुझे, ठीक है? Let's say I have a surface and on which you, let's say, move an object with force F, and let's say there is friction here. Friction. और ये force friction को balance कर रहा है, ठीक है? So when force balances the friction, kinetic friction, so then this will move, but it will move with a constant velocity, the velocity. So v1 will equal v2. Yeah. इस case में the work done will still be expressed by this formula, but this will give me a change of which energy? ये बताएं मुझे. Has the kinetic energy changed here? Yes or no? बताएं. What is the change in kinetic energy here in this example? If this is constant velocity, the change in kinetic energy is 0. Yeah. Has the potential energy changed here? No, because there is no height involved. So potential energy is also 0. अब मुझे बताइए ये वर्क किधर गया? You should know this from physics. फ्रिक्शन में क्या होता है यहाँ पे, अगर आपने कभी एक्सपीरियंस किया हो? हीट इन्वॉल्व होता है ना, so actually it is thermal energy. Okay, there is a change in thermal energy. So that's why it is safe to write this thing, that work causes a change in energy. It is not always kinetic energy, it is not always potential energy. And there is even a different although, okay, so let's not get into that. We still want to stick to rigid bodies. Okay, so let's move on to if you okay, let's change this. We can now build on this last equation, this one, and although we do integrate over some path, yeah, but we don't integrate, we don't consider time here. Okay, so if you have, let's say, a device which is providing power, which is providing energy, yeah, in the form of work, yeah, it is providing work. So you would like to know the rate of that work, क्योंकि कुछ वर्क, वो वर्क जो है ना, if it is provided at a faster rate only, at a higher rate, sorry, only then it is useful. Okay, so more interesting for us will be the rate of change of work, yeah, and that rate of change of work is what we call power. Okay, power. And if you look at this formula, remember, if W is integral of force over some path, if I remove this integral, I can see this as small work, dW. Yeah. And now I can think of this differential quotient, and this will give me power, and this I can write as F dot V. So the power at any time can be calculated by this dot product, force times velocity. Okay, force times velocity. But there is another twist to this. What if you have, let's say, something which is rotating, like a motor? Yeah, a motor will rotate things. When you rotate things, how you calculate the work done along a circle or along a circular path? तो वहां पे हम क्या करेंगे? You will, let's say, you imagine something like that, a scenario like that. You will have tangential force, T for tangential force, and this dr, the we know that in circular motion the displacement in a short interval is the same as the distance, small distance or length of an arc, and this you can write as the velocity times dt. Yeah, velocity times. But that is one way of writing it. You also know from radians, and you know that this distance r theta. Yeah, so I can simply write this as r d theta. Yeah, r d theta. We discussed this last time, that if you have a motion and circle, yeah, so this distance ds can be seen as this d theta times some radius. So radius times d theta. Now, what's the advantage of writing it in this way? because I can express this work. Let's say this work is over a circle. This path is a circular path. Yeah? So I will then say, okay, I will write from this integral f dot, I will start from this, and I can then replace it with, okay, f tangential and ds, yeah, this ds, because in tangential force, this f and d are parallel, so I can simply write the magnitudes, the magnitude of force, the magnitude of displacement, and this I can write without changing ft. I can write d, replace ds with the r d theta, so it will be r d theta, and f times r will give me the magnitude of the torque. Yeah. So the work done along a circular path can also be seen as an integral of torque, the rotating mechanism, integrated over the angle in radian. Okay, torque over the angle. So now this also allows me to write. So one thing is clear, that W can be written not only as the integral of force over a path, but also the integral of torque over a path, over angle, sorry. And if I take the differential work, this will, if I take this form, this will be t d theta. And if I now divide this by dt, so I will get, I divide both by dt, and that gives me power equals torque omega. Okay, to be more precise, is torque dot angular velocity. Yeah. So I can now write two different formulas for power. One is that power is force, the dot product of force and velocity if I am considering linear motion. But if I am considering this circular motion, I can also see power as torque dot the angular velocity. Yeah. So you just remember these two forms. And what will be the unit of torque? यूनिट ऑफ टॉर्क क्या होगा SI सिस्टम में? क्या होगा यूनिट SI सिस्टम में यूनिट ऑफ टॉर्क? बताएं.
न्यूटन मीटर.
नहीं, न्यूटन मीटर तो वर्क का यूनिट होगा ना. सॉरी, टॉर्क का नहीं, मैं पूछ रहा हूँ पावर का. आपकी बात ठीक थी, पावर का यूनिट क्या होगा? मैं असल में पूछना पावर चाह रहा था, गलती से मैंने टॉर्क कह दिया. What will be the unit of power in SI system?
Watts.
Watts, okay. और वो दूसरे में US कस्टमरी सिस्टम में?
सर
बताएं वो क्या होगा?
जॉल्स.
नहीं, जॉल्स तो US कस्टमरी सिस्टम में जॉल्स नहीं है ना. सो जो आपने वॉट कह दिया वो बेसिकली क्या है, वो जॉल्स पर सेकंड है. ठीक है. तो उसमें क्या होगा, जॉल की जगह क्या होगा? फुट पाउंड per second. This is the unit of power in US customary system. You don't have a name for it. Of course, there are other quantities. इसको आप हॉर्स पावर में कन्वर्ट कर सकते हैं by some conversions. मुझे याद नहीं है कि कौन सा यूनिट है, लेकिन some foot pound per second is equal to 1 horsepower. So let's get to the slides prepared by Maria, and she has some examples because she prepared more examples, so I'm now switching to that. So let's this example is from Wickett and Lewis. What you see on the right is a fan used to cool some electronic circuit board. So if you look at this, in spite of all the details, you can just see this as motion in a circle, yeah? The tip of a fan is moving in a circle and the radius of that circle is r. So if you see the circle here, you can see a particle moving in a circle of radius r, which is 4 centimeter. Now what you see here is 1800 rpm, yeah? So in part A, you want to express the motor's angular velocity, omega. This omega is given to you as 1800 rpm, and you want to express this into something degree per second, and then you want to express this into something radian per second. This is what they are all angular velocities, only the units differ. So let's start with this one, okay? So I start with 1800. RPM is better. It's better to write RPM as revolutions per minute, because we want to multiply this with something so that I get rid of the minute first. तो minute को मैं numerator में लिख दूंगा, ठीक है? So that I cancel it. So 1 minute, and what should I write in denominator now? How many seconds? 60 seconds, yeah? 1 minute divided by 60 seconds is like multiplying by 1, okay? So I can get rid of minus the minutes. What else do I need to do? Let's say I want to do this part, yeah? So revolution को denominator में रखूं या numerator में?
न्यूमरेटर में नहीं, डिनोमिनेटर में,
because I want to cancel it. और यहाँ पे मुझे चाहिए क्या? डिग्रीज. तो कितनी डिग्री यहाँ पे? 1 revolution is 360 degrees, yes? This will give me something in this unit. ठीक हो गया? अब अगर मैं if I want to solve this part, this one, तो फिर मुझे क्या करना पड़ेगा? सिर्फ ये चेंज करना पड़ेगा. 1 revolution is still correct, but here I need to write some things that this vector gives me 1. So radian, I need some radians. तो यहाँ पे क्या लिखूं मैं? 2 pi radians give me 1. It gives me one revolution. So this way I can solve that one as well. Okay. Now determine the velocity of the 4 centimeter tip at the fan blade. So the tip velocity Vt, which is also the tangential velocity, it's simply omega times r. And when I say Vt, I mean the speed. Okay. I only write the magnitude, which is speed. So if this was speed or the magnitude of velocity, then this will be my calculation. I'll simply take this result from this part, omega, यहाँ पे मैं लिख दूंगा या radian per second, and then I multiply this with 4 centimeter, and 4 centimeter I can get rid of centimeter by writing 100 centimeter and 1 meter, and then I'll get this by something which is meter per second. But this is the magnitude, okay? If I want velocity, just like here, then I may use the vector here, and here I need the unit vector here. So for the unit vector, I can simply choose my axis, xy. Let's say right side, it is to the right is my x, to above is my y, and the right hand rule will dictate that out of the page is k. So I can now write k here, okay? K here, and I will also have k here. So when velocity is asked, you need to be clear that your answer is in vectorial form and not in scalar form. So do you see the particle part here, that we have replaced this whole body? I mean, we cannot replace the whole body by a particle in this case because it's rotation, but we only consider the tip of the fan. Okay, हमने सिर्फ tip of the fan, यहाँ पे जो कि mass involved नहीं है, so we can't do that. If I replace a fan with a particle at the center of mass, a particle cannot rotate about its own axis, तो वो फिर गलत होगा. ठीक है, ये हम इसलिए कर सकते हैं कि we now are considering a particle at the tip of the fan, and that tip can rotate about the center. So you need to be clear about which model you are using. We are using the model of the particle model, but for the tip of the fan and not for the whole fan. ये मैं skip कर रहा हूँ क्योंकि हम किसी और स्टेज पे कर लेंगे. I think we are not yet ready for this. One clarification is important here, that because work is an integral, so many times you see that integral as some area under the curve. अब ये जो area under the curve वाला concept है, ये real calculus में होता है. And in real calculus, you have the x-axis and you have some scalar quantity here. So अगर ये scalar force है, the magnitude of the force, I'm not writing the arrow here. And if there is some distance, remember this is also scalar, this is scalar, this is scalar. तो फिर आप कह सकते हैं कि okay, on the x-axis I have my distance s, on y-axis I have the magnitude of the force, and okay, because they are both scalars, so I can talk about the area under the graph. Lekin if I go with the original definition or the original form of work, which is the vector force dot product displacement along some path, now this should not be seen as the area. The area under curve वाला picture यहाँ पे नहीं चलेगा. ठीक है, क्योंकि this is the integral along the curve. आपने अगर कैलकुलस में पढ़ा होगा, उसको कहते हैं line integral. क्या? Now line integral is an integral along the curve. Okay, that is not area under the graph. Area under the graph का concept वहाँ पे नहीं valid होता. ठीक है, that is something we need to keep in mind. Scalar में convert करने के बाद आप फिर कह सकते हैं सारा. So because we saw the result that in many cases, okay, the work done on a system leads to a change in some property which we call energy. That energy takes different forms. Mechanical energy includes kinetic energy and potential energy. Okay, heat and thermal energy, electrical energy, chemical energy, all these different forms. Okay, and you also have a concept of mechanical efficiency. And mechanical efficiency, you simply check the ratio of work output and work input. Work output by the system and work input to the system. And I use work because work is the useful form of energy. Useful form of energy. Thermal energy is not a useful form of energy in the sense that you cannot use all of the thermal energy for work. Definitely some part will be not available for work. So what we do is that if it is still possible to have work output in the numerator, and here instead of work input you can have thermal energy or heat. You can have heat here, heat input, and then this efficiency will be called thermal efficiency. Okay, so ये बात जरूरी है कि हर mechanical efficiency word आप कब यूज करेंगे? When both the numerator and denominator, क्योंकि सिर्फ energy लिखना काफी नहीं है. यहाँ पे तो आपने जनरल बात लिख दी ना. अगर यहाँ पे आपने work लिख दिया और यहाँ पे भी work लिख दिया तो फिर ये mechanical है. अगर ये work है और ये thermal है तो thermal efficiency है. ठीक है. And there are some other interesting examples where, for example, an air conditioner or heater, home cooking heater, उसमें इनपुट क्या होता है मुझे बताएं। इनपुट की एनर्जी एनर्जी किस फॉर्म में होती है एन में, ये बताएं कौन सी फॉर्म होती है। घर में जो आप एयर कंडीशनर या यूज करते हैं, इलेक्ट्रिक हीटर, तो एनर्जी इज इन द फॉर्म ऑफ इलेक्ट्रिकल एनर्जी। और electrical energy you will see in thermodynamics in that course that electrical energy can also be considered as work. Okay, so yes, efficiency उधर denominator में you do have electrical work, लेकिन न्यूमरेटर में क्या होगा, आउटपुट। एयर कंडीशनर या हीटर का आउटपुट क्या होता है बताएं। Is that useful work or not? एयर कंडीशनर की जो आउटपुट एनर्जी होती है वो थर्मल एनर्जी होती है, या energy taken out of the room or energy taken into the room, but in both cases it's thermal energy. Thermal energy divided by work is not called efficiency, उसको efficiency नहीं कहेंगे, उसका thermodynamics में कोई और नाम है जो कि आप स्टडी कर लेंगे। लेकिन remember, for something to be called efficiency it is important that the numerator is work. Okay, if the denominator is also work it's mechanical efficiency. If the denominator is thermal, then it's called thermal efficiency. वो दो टाइप के efficiencies आपको मिल जाएंगे, लेकिन it is not possible that in the numerator you have thermal energy and you call it efficiency. उसको efficiency नहीं कहते, ठीक है, उसका एक और नाम है। And I don't want to confuse you now, but simply remember that that is not efficiency. So we can now solve this problem. You have a hoist which is run by a motor. So this is your hoist and it is taking energy from the motor. Okay, ये मोटर इसको एनर्जी दे रहा है। So because electrical energy is work, so we can say okay there is work input. Work input is here, and then it has work output as well, because it is used to exert a force of 500 newtons. So it can apply a force of 500 newton. By force I mean the magnitude of force here, and it raises a load through a height of 20 meters. ठीक है, height of 20 meters, and the magnitude of force is 500 meter. So the work done on the load, is F times H, and that is 500 newtons times 20 meters, and that is I think 10,000 joules. You can also say 10 kilojoules. Now this 10 kilojoules, can you tell me it is work in or work out? If this is your system host, it is producing that work, so it is work out. Okay, work out is 10 kilojoules. Now because it involves a motor and a gearing, so the motor's efficiency is 80%, and the gear's efficiency is 75%. Now if this is Wn, calculate the input energy. This is the unknown. Okay, we want to calculate the input energy. So here 80% of that energy, 0.8 times Wn will be available here. Not all of the energy is available here at this point. Now when the losses in the gear are incorporated, the output energy for this you have available 75% of the energy available, which is this. Yeah, so you started with input energy, 80% of it was available to the gear, and 75% of this reduced energy is now available to the output. So it means that, and the output we know is 10 kilojoules. So Wn, the input energy, will be 10 kilojoules or 10,000 joules divided by this product, 0.75 times 0.8. This is the overall efficiency. You can also think of this product 0.8 times 0.75 is the overall efficiency, which is I think something nearly 0.6. Okay. Okay. Is if you have understood my comments just made a while ago, तो इस इन definitions में कौन सा ठीक है और कौन से में गड़बड़ है? This is okay, yeah, because power is always used for the rate of work. Okay. Now energy, because energy is not always the useful form of energy, thermal energy भी हो सकती है, तो वहां पे आप वो उसको पावर नहीं कह सकते. So this has to be useful energy. Okay. And useful energy is the work. So let's solve this problem here. A lorry, I think this is from the other book, Principles of Mechanical Engineering. A lorry is traveling at a constant velocity of 72 kilometers per hour. Yeah, speed basically. So the speed is given and it is constant. It is not changing. That is, the speed is 72 kilometers per hour. The force resisting motion, there is a resisting force which may be friction or air drag or whatever, liquid friction. That force which you must overcome is 800 newtons. Yeah, resistive force, RES. So for the velocity to be constant, the applied force must equal the resistive force in magnitude. Yeah, they must be opposite in direction. So the applied force will also be 800 newtons and the net force is 0. Calculate the tractive power necessary to keep the lorry moving at constant speed. तो लॉरी को जो ट्रैक्टिव पावर चाहिए, let's say this is input power n, वो कितना चाहिए? Now that input power is the applied power force times velocity. Now because applied is also equal to resistive force, yeah, and magnitude, because it has to be at constant speed and it's the same speed, yeah, it's the same speed. We just take the speeds. So we simply plug those two values, yeah, here. 800 newtons multiplied by 72 kilometers per hour, and you can of course get rid of hour by 3600 seconds and get rid of kilometers by 1000 meters, and you will get your calculation, and at the end you will have watts. Okay. Okay, we have this formula. We already discussed this. Torque times angular velocity if you have rotation, and in linear motion you have force times linear velocity. Okay, we can now move on to the last example, and there you have again from Wickett and Lewis. So at full throttle, a four-cylinder automobile engine produces 149 foot-pound of torque. Okay, so you have torque, the magnitude of torque, which is 149 foot-pound of torque, and this happens at a speed of 3600 rpm, and you can convert this 3600 rpm into because I can write this as revolution per minute, so I can do that calculation again, that I get rid of minutes first, second, and then I get rid of revolution by 2 pi radians, and this will give me something in radian per second. Now, how much power does the engine produce? So power is T times omega. I'll make this calculation, okay? 149 foot-pound and then this calculation in radian per second. But I need to make sure that I get my answer in horsepower, okay? So let's see horsepower. कि horsepower हमारे पास इस बुक में ने horsepower का कोई ना कोई टेबल दिया होगा. Horsepower. Yeah. So you see horsepower. I will provide a table, but what we discover here is that 1 horsepower is 550 foot-pound per second. So we can now make use of this. 550 foot-pounds per second. I do get foot-pound per second from here, so I need to put it here, so get in the denominator to get rid of it. Foot-pound per second, 550 will give me 1 horsepower. Yeah. So I can get rid of foot-pound per second. Foot-pound per second. Radian is dimensionless anyway. Yeah. Hello. वालेकुम सलाम. मेरी क्लास हो रही है. अच्छा. So this will, yeah, I can get my answer in horsepowers. Okay. Do you have any questions so far? Because I think we still have time left, so I can cover one more thing which I did in the other lecture. कोई question है तो पूछ ले इसमें. Because then I will switch to that new topic. That new topic, actually it's not a new topic, it's just a continuation of that relationship which we discovered in the beginning, that work done on an object or on a body, which is of course F, the integral of force over distance, or the integral of torque over the angular displacement. It can be any of these two. And this leads to a change in energy. And that change in energy in some case was kinetic energy, delta Ke. In some case it was gravitational potential energy. I'm writing GR because it was gravitational. In some case it was a change in thermal energy. And now we want to consider another example where it is another form of potential energy, but it's in fact elastic. It's called the elastic potential energy. You already know that from materials. Okay? So you remember that if you have a deformable body, okay, and the proportionality limit, and if you have, let's say, length L, and it changes to delta L under the action of some force, tensile force, you would like to know the work done by that force. And that force, that work done, so of course, work done by this tensile force is F tensile and d x, let's say it's in the x direction, and you would like to know, okay, this this is a change of some energy, so what is that change? So if we assume that region of proportionality जिसमें हम elastic को कर सकते हैं, so you remember we can apply Hooke's law there, and Hooke's law में this force will simply be equal to k times x. Okay, k times x. We don't write the minus sign because that minus kx will be the restoring force and this is the applied force. We are now considering work done on the system. So on the system के लिए उस minus kx को cover यही kx करेगा, ठीक? And if I now integrate this, I'll get half k x squared, and if you integrate this between 2 points x1 and x2, so I'll get half kx2 squared minus half kx1 squared, and this is a change in the elastic potential energy. Elastic potential energy. Okay. So in all these examples, the rule is the same, that if you have a system, a body, and the external world is working on it, yeah, so that work will result in a change of some form of energy. That energy can be kinetic, can be potential, gravitational potential, elastic potential, or thermal potential energy. Okay. So do you have any questions so far? I think ये यहाँ पे मैंने वही examples conclude किए थे. We already did that. We still have time left for questions because it took me more time to cover these examples in the other lecture. Maybe there were more questions. यहाँ पे आपके इस lecture में questions नहीं है, so you can use this time to ask questions. So make sure that you write P here, okay?